We are very glad to have you here. The Academy of Science is very honored and proud of your presence here. But let me tell only two things. One thing is the Lagrange is there, and probably you already see. And so it's a meeting between Lagrange and Einstein. At least one person is here. And the second thing, more serious, is I read this afternoon actually, before coming here, your paper about the map in the universe and 2010 lecture at Russell lecture, that it was co-author also, I think, no? Who's the author? Arnaldo. Antonaldo, sorry, Antonaldo. And I would like to read only the final words, because I think they are very relevant for our academy, for the academy in general. It tells the following, if I find it. It's the final words, actually. And I would encourage senior people. Here, some of us are senior, some of us. Yeah, no. Not you. No. I don't mention you, but some of us are. To give some thought to the structure they have set up that so discourage risk-taking. And we all need to ask ourselves some hard questions about the kinds of opportunities we provide in science and the way we evaluate the most creative young scientists. I think this is a very important problem that everybody of us have. And the final word is the universe is startlingly vast. And just as large-scale patterns in the universe were a surprise, there will be more and more surprises to come. I added it, but it's written. Some of these surprises will, I hope, still be in work done by imaginative individuals looking in neglected corners where important questions can be found and answered. I hope we answer very soon some of these questions, but I think this is really something that applies to all scientists, not only to astronomical science. Thank you very much for your...
Okay, I start with a short presentation of some of the highlights of Margaret, Dr. Margaret Geller, and then I leave to Antonaldo, a more personal discussion, because they have been working together for some time. So first of all, I repeat the privilege of the Academy to have this very honorable guest today that is going to take us around the universe with this presentation. She started her study of the universe a few years ago, and actually she was responsible for establishing a new research field in cosmology. So her idea, the first time I met her in Cambridge, England, and at that time we were, just talking about science a little bit, and I remember that she was planning to map the universe. That was her dream, actually. And I met her again in the other Cambridge, Massachusetts, where she was staff in the Harvard Smithsonian Center for Astrophysics. And at that time, she had already really published the first map of the universe. And actually, she had we can run some of this is the movie that she presented afterwards, on the basis of this scientific data. Actually, this was a movie that she made in 1992. The title was So Many Galaxies, So Little Time. The important thing was not only the presentation of the movie itself. It was the very first experiment using the numerical codes for visualizing data, and to give to the public also the possibility of understanding how the universe was made. And in particular, it was important to to show how also for the scientists it was important, this kind of visualization, because you really have a real view. The first time I remember in the movie, she discusses actually in detail the fact that the first time she saw the movie, it was clear that there were voids, that the galaxies were not distributed evenly in the universe, but they were connected in filaments, in groups, and whatever. And so that was the important thing. It was really, her work has been really pioneering, not only in terms of science, but also in the part that has to do with opening the eyes of young students to science in a different way. Actually, Margaret has been, has created a lot of important scientists who had a wonderful career. One of them is Antonaldo here, who was a student. No, the career is okay for the moment. We will see what's going on later on. But so she has actually a talent. My impression is a talent of, inspiring people. That was the thing that I learned from her and meeting her in many years. And I just mentioned that she is a member of the National Academy of Sciences, of the American Academy of Arts. She has received many international awards, but in particular I mentioned the fact that on Monday she will receive an honorary degree in physics at Harvard University, which is very important. So I don't want to say anything more. I thank Margaret for being here and for helping us actually to create a cosmology group here in Torino. That's the important thing. And so I leave to Antonaldo to elaborate on the evolution of cosmology in Torino also.
Well, thank you. Thank you, Attilio. Thank you all for being here. It's a real pleasure to introduce Margaret. I will be very short because I don't want to take time out of Margaret's, Dr. Geller's talk. Attilio actually has told most of the relevant points about the curriculum of Margaret Geller. I want to add that the movie you're seeing shows one of the most outstanding achievements of human being on the human beings, because it's the largest patterns that human eyes have ever seen. Those are patterns of the galaxy distribution that extends for more than 300 million light years. And it wasn't, the community and humankind wasn't aware of these large patterns in the distribution of the galaxy until Margaret Geller found them in 1986. And in fact, that discovery made a huge impact on the media. Margaret Geller's discovery appeared on the front page of the New York Times, and the Encyclopedia Britannica has to he wanted to present these results in its pages. So there is a slide. This size of the universe appears in the Encyclopedia Britannica at that time, and of course all this discovery was awarded many prizes, and so Margaret Geller kept making impressive discoveries in the following years, including the dynamics of classes of galaxies and pioneering work on the connection between galaxy properties and the environment. And recently she also collaborated in discovering hypervelocity stars. So the distribution of galaxies is not the end of the story in Dr. Geller's career. So it's really a great honor to have her here. And as Attilio mentioned, she also is very gifted in making the scientific achievements open to the public. She's a great speaker, and she also a very gifted writer. In fact, I only tell you this story, and then I quit my my introduction. The first time I went to the Center for Astrophysics and met Margaret Geller, I had a draft of my first paper on groups of galaxies, and my English was very poor. It has improved a little bit ever since, but not that much. So Margaret Geller and I sat in front of the computer, and she basically rewritten the paper, pretending that actually she was suggesting a few modifications to the text. And then I was there for a few weeks. Then I came back here because I had to finish a few things. And then I went back to the Center for Astrophysics a year later without touching that draft of the paper. And she read it again. And she said, well, Antonaldo, your Italian has improved a lot. And you wrote it very well. And I said, well, actually, that's what you wrote. I didn't touch it. So just to tell you that she also is very humble too. So and so you'll see now that she's a great speaker too. And the title of her talk is telling much about how she, the depth of her knowledge of physics and astrophysics. So, and until you remember that this Monday Margaret Geller will be awarded the honorary degree in physics at the University of Torino. Of course, you all are welcome to participate in the ceremony that takes place at 2:30 p.m. In the rectorato of our university. So I don't want to take more time, and I leave Margaret Geller starting her talk. So I had to switch.
Well, 3 flattering introductions are a bit too much. Thank you for all these very kind words. I must say, it's really awe-inspiring to be here and to think of all the history that's come before. This evening, I'd like to tell you about how, in this very bizarre universe that we live in, Einstein meets Lagrange. Einstein meets Lagrange in helping us to map the way matter is distributed in the universe. We can use the theory of general relativity to map the matter distribution using what we call gravitational lensing. And of course, we can use classical physics as formulated by Lagrange to measure the matter distribution. And we can compare the two and ask whether they give us the same view. And I'm going to talk about the first steps toward doing that. We live in a very bizarre universe. Nearly all of the matter in the universe is not even the stuff we're made of. 87% of it is what we call non-baryonic dark matter. And we still, after 80 some odd years since the discovery of the dark matter, we still have no idea what it is, even though we know pretty well where it is. Galaxies, like the ones you see in this very deep Hubble Space Telescope image, light our exploration of the universe. And of course, the galaxies that we see, or the stars that give the light that we see, are made of the kind of material we're made of, baryons, which constitute a mere 13% of the matter in the universe. To make matters even worse, more than 70% of the total energy density of the universe isn't any kind of matter. It's something called dark energy, which we also don't understand at all. We use these parameters or these quantities that I'm describing to you to make a basic model for how the universe works and how structures like our own galaxy develop in it. But fundamentally, we lack a fundamental understanding of the constituents of our universe. The universe at large is very different from the solar system where we live. In the solar system, most of the matter in the solar system actually gives out light of some kind. Jupiter, most of the mass is in the sun and Jupiter. Jupiter is still collapsing, and it thus gives out more energy than it receives from the sun. So only 0.1% of the material in the solar system doesn't give out any light. So the universe at large is very, very different from our local neighborhood. So as I said at the beginning, we're going to use two different approaches to try to trace how matter is distributed in the universe. And the one that I actually do, and I've spent much of my career doing, and so often with the help of Antonaldo, is to use the classical mechanics as developed by Newton and primarily actually Lagrange. So Newton developed the original theory of gravity in the period 1666 to 1686. And in fact, Newton was a rather poor student, but he was home from Cambridge to avoid the plague during the time he developed the theory of gravity. And it took him a long time to publish because the theory didn't fit the observations. The reason it didn't fit is the distance to the moon was so poorly known that the inverse square law didn't fit. Really is amazing. Lagrange, then Newtonian, in the Newtonian formulation of the theory, made it very hard to apply because it's all vector quantities, forces, and so on. And Lagrange, in a brilliant application of mathematics, recast the theory of gravity in the form that we use it today in terms of potential and kinetic energies. And he did that while he was living in Germany in the period 1772 to 1788. This recasting of the theory of gravity enabled people to begin to make very sophisticated calculations about the motions of planets and in the solar system, and to even make predictions. One very interesting story that is based really on Lagrangian mechanics is the discovery of this planet, Neptune. Neptune is interesting because initially the way it was discovered, or the way people understood there was another planet, is that there were irregularities in the orbit of Uranus. And interestingly enough, at the time, people interpreted those irregularities in two different ways. One, something is wrong with the theory of gravity. Two, there must be a dark planet. So, in a way, that's rather similar to the situation we're in today. We have a universe full of dark matter. We haven't been able to figure out what it is, even though we've looked very hard. So, maybe there's something wrong with the theory of gravity. And more people are exploring that. Now, in the case of Neptune, the prediction was made in the period 1845 to 46, and it was discovered very promptly after the prediction. And I'll tell you a little bit about the story because it is a story about the foibles of science and about senior people versus junior people. So in the 1840s, a young man named Adams, who was an undergraduate at Cambridge University in England, got curious about these perturbations or these irregularities in the orbit of Uranus. And he decided to figure out whether there might be another planet, and if so, could he predict where it was? So he did that. And he sent his calculations to Airy, a man who was the Astronomer Royal of England. Airy thought that there was something wrong with the theory of gravity. Not only that, this was a mere undergraduate. So instead of having a look, he sent Adams another problem to do. Adams was offended and refused to do the problem. Meanwhile, in France, Arago, who was the director of the Paris Observatory, suggested to Leverrier that maybe he should calculate whether there was another planet, and if so, where was it? Leverrier did that. He sent it to Airy, and since Leverrier was a senior person, Airy asked Challis, then the observer at Cambridge, to have a look. But Challis was incompetent, so he couldn't find it. So Leverrier, being impatient, sent his prediction to a man named Geller, who was in Berlin, and he found it within a degree of the predicted position. This is a cartoon that a friend of mine who's a historian pointed me to, a cartoon of the time. So you can see it's a cartoon that was not made by the British. So you can see the British are in the dark looking for something that was predicted, but they couldn't find it, and the French are very smart. They look in their calculation and they find it right away. So this was the story of the discovery of a planet in the solar system. Now, in the case of the universe at large, dark matter was discovered by a very odd character, Fritz Zwicky. I used to be fascinated by him when I was young. I never met him. He was still alive when I was doing my work for my dissertation. Zwicky discovered dark matter in the universe by measuring the velocities of galaxies in a cluster of galaxies called the Coma cluster. So he measured their motions relative to one another. He could compute the size of the cluster, and he could compute the total kinetic energy. And he compared, then he just applied classical physics a la Lagrange. And what did he find? That there was 10 times as much material in the cluster as he could explain by the stars necessary to give out the light from the galaxies. So since 1933, dark matter has been with us ever since. I need to stop for a moment to tell you a story about Zwicky. When I was a student working with Jim Peebles at Princeton, Jim Peebles sent Zwicky a letter. Jim was about to analyze catalogs of galaxies made by Zwicky. So Jim sent Zwicky a letter asking Zwicky what Jim might learn by analyzing these catalogs. Zwicky sent back the picture shown here. I once told Jim that I would like to meet Zwicky. He said, "No, you wouldn't." Anyway, Zwicky was really a giant of 20th century astronomy, and people liked him a lot more after he died than when he was alive. So here is a classical picture of the Coma cluster of galaxies. So it's just grayscale. All the fuzzy objects you see are galaxies comparable in mass with our own Milky Way. Amazingly enough, Zwicky measured the velocities, and I'll show you how that's done in a little while, but he measured the velocities of 8 of these galaxies. Only 8. And he got nearly the same answer we get today, measuring 1,000 of them. So that's how the dark matter was discovered, by looking at this cluster of galaxies, which is a few 100 million light years away from the Earth. It sounds like a big distance, but it's small compared to the 14 billion year lifetime of our universe. In 1937, Zwicky made yet another leap. He wrote a paper saying that, yes, he had found that the Coma cluster was much more massive than you could explain by adding up the stars responsible for the light, but he was one of the few people working in the United States who really understood Einstein's theory of general relativity and its implications. So he predicted that we would ultimately know the masses of objects in the universe from the phenomenon of gravitational lensing. 1937, the first gravitational lens was discovered in 1979. And Zwicky died, sadly, in 1974. But it's amazing. So, of course, as you all know, Einstein wrote down the theory of general relativity in 1915, and the content of that theory is really that gravity is geometry. And as John Wheeler liked to say, matter in the universe distorts the geometry of space, and the geometry of space tells matter how to move. So here you can see Einstein surfing on the gravitational waves. Einstein's theory of general relativity predicts that mass concentrations will bend light paths as they travel through this puckered, curving space, which is changed by the presence of material in the universe. So here's a small schematic to show you what happens. So here's a mass, and you can see it makes a little dip in the gravity of space, and you see a source, and the light path is bent as it travels through this curving space. So the apparent position, of course, of the object is displaced from its true position. So you can imagine if you rotated this image around, you would see in 3D, if you have a point source behind this mass, the image will be a ring around the center of mass. And Einstein actually predicted the existence of these Einstein rings. Well, it happens. Oops. So first, let me show you a schematic, and then I'll show you the observations. So this is a schematic which gives you an idea of the way that a mass concentration in the universe distorts background objects. So each of these blue points represents a distant object, a faraway object in the universe. And the points, undistorted, you can see them in the corner, they're just tiny round points. The pink indicates the mass concentration projected on the image of a cluster of galaxies. Now, of course, in the universe, you can't move the background sources along behind the cluster, so the cluster is in front, and the background sources are behind. So now you move the background, and as it moves, you can see that near the mass concentration, you see these highly distorted images, pieces of rings. This is called strong gravitational lensing because the distortion of the object is large, and at large distances there are tiny distortions. But in fact, because there are so many galaxies in the universe, even though the distortions are as small as 1%, we can actually measure them and map the matter distribution in the universe. Now, do we see these things? We do. This is a spectacular demonstration of an Einstein ring. So a fellow named Adam Bolton looked at a lot of galaxies in the universe. These are galaxies called on the left, you can see the yellow is the light distribution from a galaxy which is no longer forming stars. So unlike our Milky Way, this galaxy isn't forming stars anymore. They're called elliptical, they're often elliptical in shape. So what he did was he went through a big database and looked for all the galaxies like this, which had unusual features in their spectrum indicating that there might be something else along the line of sight. And then he imaged these objects with space telescope. So in the left-hand image, you can see a very faint ring. And if you subtract the galaxy, you can see on the right the ring. What is that? It's an image of a more distant galaxy. So the yellow, the nearby galaxy, is at a distance of 2 billion light years. In other words, we see that galaxy as it was 2 billion years ago. The background object is at a distance of about 5 billion light years. So the foreground galaxy magnifies and distorts the distant galaxy. And by studying the light from the distant galaxy, we can actually learn something about these distant objects. So this is a very simple case where the very straightforward prediction of Einstein's theory is borne out in the universe on large scale. The matter distribution in the universe is very complex. So here's a real cluster of galaxies, very different from the one in the video that I showed you. So every fuzzy yellowish object here is a galaxy resident in this cluster, which is about 2 billion light years away. And you can see that there are a bunch of arcs. It looks like there's some problem with the camera or some fault in the camera, and they're all different colors. Some are blue, some are red, and they tend to be around some of these fuzzy objects. What are those? Those are images of distant galaxies. And the more distant they are, the redder they are. So this cluster, as I said, is 2 billion light years away. The galaxies that are lensed are all more than 8 billion light years away. More recently, with Hubble Space Telescope, people have been able to use clusters like this. They are sort of cosmic telescopes. People have been able to use clusters like this to image galaxies at the time of their formation. So they've been able to image galaxies as they were a mere 400 million years after the Big Bang. So they've been able to image very young objects by using this technique. So this is strong gravitational lensing. What I'm going to talk about is weak gravitational lensing that you can't see by eye, because here the distortions are huge. They make these big arcs. Weak gravitational lensing, the change in the shape of an individual image is 1%. But there are millions, billions of background galaxies. So you can measure those distortions and make a map. So here's a piece of a deep image of the sky, one that we use. And here again, every fuzzy object, so this is an image from the ground. I've been showing you images from Hubble Space Telescope. So this is a fuzzier image from the ground because, of course, the atmosphere distorts the image. The advantage of going to space is you don't have that distortion. So here again, the yellow objects are these red and dead elliptical galaxies which are no longer forming stars. And the bluish, whitish objects are objects like our own Milky Way. So the yellowish ones tend to live in dense regions of the universe, clusters of galaxies like Coma, and the bluer ones tend to live in lower density regions. When you see an image like this, you have no way of knowing how far away the galaxies are. So everything is projected on the sky regardless of its image, of its distance. Now you might guess that the galaxies that are bigger, they appear bigger, are closer to us than the galaxies that appear smaller, or the ones that are at the same size, are the same distance. And here you can see these very tiny fuzzy objects. And in this tiny region of the universe, which is about 1/10 of the area covered by the moon or so, there are thousands of faint galaxies, and we can measure their shapes. Now, we also would like to know how far away the galaxies are, and that's what I do, and I'm going to show you how we do that. So, as most of you know, in 1929, Edwin Hubble discovered that we live in a dynamic universe, that galaxies appear to recede from us with velocities which are just proportional to their distance. And Einstein tells us that the reason that it appears that way is this very weird thing that the space between the galaxies is stretching. As light travels through that stretching space, the wavelength of light also stretches. So the light is shifted to longer and longer, redder and redder wavelength. So the way that we measure the distance to the galaxies is to measure these shifts to the red. For faint galaxies like this, you need a large telescope because we don't want to take just a picture. We have to spread the light out into its colors, and so you need to have a large telescope to collect lots of light. So this is the telescope that I use. It's called the MMT because when it was built, it was the multi-mirror telescope, and as you see, it only has one mirror now, but it's still called the MMT for unknown lack of creativity, I guess. I don't know. Anyway, it's now a telescope with a single 6.5-meter mirror, which you can see the primary here looks sort of dark blue. Light comes from the distant universe, travels for hundreds of millions, billions of years. It really is amazing. It travels all this way, doesn't hit anything, ends its journey, striking our CCDs and our instruments. So it hits the primary, is reflected up to the secondary, and you can see there's a hole in the primary, and behind the primary is an instrument that detects the light. The instrument is a marvel of modern engineering, as many astronomical instruments are. One of the things that I find really fascinating about this instrument, which is called a hectospec, is that this instrument, like many astronomical instruments, uses the finest technology we have to observe the largest system we know. So what are you looking at here? Well, you can see that there are a whole bunch of metal probes, and there are 2 robots. So each of these metal probes that make these radial probes carries an optical fiber, like the ones that carry your internet. These optical fibers end in a little prism that enables them to look up at the sky. And the positions, we measure the positions, the fibers are placed at the position. Each fiber is placed at the position of one of those faint galaxies in the image that we measure very carefully. The robots place the fibers in the focal plane of the telescope, and they do that in 5 minutes. Now, you might think that's a long time, but to measure these redshifts, we expose, so we're sort of taking a picture of the spectrum of the galaxy, we expose for an hour and a half. So this, and I might also mention that the light is spread out into its colors in what we call a spectrograph that sits on the floor. So these optical fibers run for 25 meters to that spectrograph. So we spread the light out into its colors. In every galaxy, the spectrum contains a fingerprint of the ions and atoms that are in the atmospheres of stars or in the medium between the stars in the galaxy. Now, hydrogen is the most abundant element in the universe. And so, in many galaxies, we see the emission lines of hydrogen. This is the H-alpha spectrum of hydrogen. You can see it stretching So the H alpha line is the red line. In the laboratory, you measure its wavelength at 6,563 angstroms. But when we see it in distant galaxies, it's at a longer, redder wavelength. And here you can see the rest of the Balmer lines shifting according to their redshift. So what we do is we measure the displacement of the wavelength. We measure a wavelength in the spectrum we observe, and we measure the difference between that wavelength and the laboratory wavelength, and that tells us the redshift. And we do that. I've done that, I hate to say, for hundreds of thousands of objects, but when I began my career, I think only about 1,000 redshifts were known. Today, millions have been measured. So, once we've measured these redshifts, we know how far away the galaxies are. So here's an image taken with the 4-meter telescope on Kitt Peak in Arizona, and this is an image of a cluster of galaxies at a distance of about 3 billion light years. And we know what it is because we measured the redshifts of every one of these bright objects that you can see in this image. So, and we know that this one is 4 billion light years away because we measured the redshifts of all these objects. So we know how far away the galaxies are. So now we're not stuck with just a 2-dimensional image. We can make a 3-dimensional map, and here it is. So we've measured these redshifts for galaxies in a 4-square-degree region of the sky. So just for normalization, the moon covers 1/4 of a square degree. So the region we've mapped covers 16 times the area of the sky covered by the moon. Each of the points in this display represents a galaxy comparable in mass with our own Milky Way. And even in this small region, you can see the characteristic structure of the universe, where you have clusters of galaxies. The red objects are the ones that aren't forming stars, and the blue objects are ones that are still forming stars. And you can see lots of things in this display. One is the red objects tend to be mostly where there are lots of other objects, and the blue objects like to be where there aren't very many. And you can see that there are very dense regions and holes, and the dense regions are where the clusters are, and the holes are these so-called voids that Antonaldo measured. And you can see the clusters are, now we have it in terms of redshift rather than the distance, but you can see that there are regions where there are these red objects. So now we have a map. We know the distance to the galaxies, and we actually, when we measure these redshifts, when there's a system of galaxies like a cluster, not only do we know how far away it is, but we also know how rapidly galaxies move relative to one another within the cluster. So, back to Lagrange, we can measure the masses. And so we can do that. So we can make a map now of where the mass is. We can project it on the sky and make a map of where the mass is, not where the galaxies are. So you saw the pictures that tell you where the galaxies are. Now I'm going to show you an image of where the mass is based on the measurement of all these velocities. Here it is. So on the left, this is a map of each side of the image is 2 degrees across. And what you see here are these red regions are where the clusters of galaxies are. So this is where the mass is, and the light blue are less massive structures, and the dark blue are empty regions where there isn't much material, at least as projected on the sky. Now, okay, this is Lagrange. Now, there are 1 million faint galaxies in the 4-square-degree region. We measure their shapes, and we make a map. Einstein. Here's the map. So you can see 3 clusters here, 3 clusters. Okay, you can see in the lower right of each image, you can see there's a correspondence. Now, you say they look different. That's because it's hard to measure something that's distorted by only 1%. So the map on the left is not very noisy, and the map on the right has a lot of noise. Not only that, but our redshift survey, we measure the redshifts of galaxies we only measure them over some range. We only measure them to a distance of 7 or 8 billion light years, and this map might image more distant structures that we don't see in our redshift survey. Now, of course, we can make a quantitative comparison between these maps, and it tells us, in fact, that what we get by applying classical physics and what we derive by applying gravitational lensing, the maps are very similar. And the distribution of dark matter, a material that we measure on these large scales, on scales of 1 million or more light years, is very, very similar. Now, when we do a survey like this, we have not only the velocities of galaxies, but we can also tell whether the objects are forming stars or not. Galaxies that are forming stars have what we call emission lines in their spectra. Galaxies that aren't don't. So we can ask, how do different kinds of galaxies trace the matter distribution in the universe? And so now I'm going to show you what we learn when we do that. So there are a number of things we can do. So here you see the entire survey projected on the sky. But we know how far away the galaxies are, so we can slice up this map. We can ask, which of these peaks are how far away? Which one is which? So let me show you how we do that. So here's a schematic. So you can see the redshift survey, and now what we're going to do is take a box in the redshift survey. We can do that. So we're going to take one that gives us a view of what this piece of the universe looked like 3 billion years ago. We're going to take another box. What did it look like 5 billion years ago? And we're going to make a map. And actually, at each age, we're going to make 2 different maps. One based on galaxies that don't form stars anymore, and one based on galaxies that are still forming stars. So let's check out 3 billion years ago. So here's one of the clusters that's 3 billion light years away. You can see that it has red objects, and you don't see any blue objects around the red ones. Now let's look at the maps. So the central map shows you the whole lensing map, everything mushed together. On the lower left is the map based on galaxies that are no longer forming stars. So you can see there are two big red blotches that correspond to 2 clusters. So only 2 of these 3 clusters are at that depth in the universe. Now we can look at the star-forming galaxies. On the right, nothing. So at this time in the universe, the distribution of material is traced predominantly by objects that are no longer forming stars. They're old. But the situation is not the same when we go to 5 billion light years. So here's a picture of a cluster that's 5 billion light years away. And here you can see that there are blue objects that appear to be very close to the yellow ones. Are they at the same distance? Well, actually, they are. So if we make a map, we have on the left the map galaxies that are dead. And you can see there are some peaks that correspond to the peaks in the lower left. And you can see that the star-forming galaxies also contribute to the signal at this redshift. It's interesting that you can see this even with this weak lensing. This is the first time it's been seen in this way. It's known from other avenues of investigation that as you look to earlier and earlier epochs in the universe, more and more mass is tied up in galaxies that are forming stars. But these lensing maps tell you the same thing. So with a redshift survey and a lensing map, not only can you map where the material is, you can map what kinds of objects are tracers of the material. I forgot to mention that also there are regions where you don't see much signal in the lensing map, and you don't see it in the map that we predict from the redshift survey either, so you can also see the low-density regions in the universe. Now, of course, with better data, you can always do better. And in 2020, ESA, the European Space Agency, will launch this satellite, Euclid, and it will have an advantage over imaging from the ground, of course, because you don't have the distortion of images. And it will survey a very large region of the sky, 30% of the sky, and it will identify something like 10 billion objects, and shapes, these tiny distortions, will be measurable for about 1 billion of them. So we measure 1 million, this will do 1 billion. So you can answer different kinds of questions because this survey will be deeper, and it will also measure redshifts for some millions of, I think tens of millions of objects. And so you'll be able to ask different kinds of questions. You'll have a redshift survey that goes deeper into the universe than ours, so you'll be able to see the full range of the space in the universe that's imaged by the lensing map. And the lensing maps will have greater resolution, so you'll be able to look in detail at the outer regions of clusters where you can make very sophisticated tests of the theory of of different theories of gravity, as Antonaldo has been doing with his colleagues. So it will be very exciting to see how these tools, how this geometry is used more and more in comparison with the classical physics. Every time I think about imaging in space, I'm reminded of an experience that I had with Vera Rubin, and I'd like to close this lecture just with a short story, a memory of her. She and I were both present at a lecture given by Neil Armstrong. And Neil talked, of course, about his experiences in landing on the moon and so on. And people at the end were asking very technical questions. And Vera Rubin had a way of answering these seemingly simple but very deep questions, which often are the ones that are really important in science and everything else. So Vera raised her hand and she asked, "What does the sky look like from the moon?" So Armstrong paused for a moment and he said, "Well, when you're on the moon, you have all this stuff around you, so you don't have much of a field of view. But you can look at the Earth hanging there against the black of the sky with the points of light. But the twinkle is gone." I hope that all of us can continue to work together to preserve the twinkle. Thank you so much for this great honor.
What they?
May the 5th, we should have another astronaut coming here, Duke. So we'll ask the same question to see how we answer.
Got the same question. Well, thank you, Margaret, for your lecture and for very informative and touching some places lecture. And if anybody from the audience has a question for Margaret Geller, she's happy to take it.
So we wait question from the young students.
If you can.
Yes.
The young student.
Okay, you mentioned that the big problem is to understand whether we need dark matter or we have to modify relativity.
Yes.
When you compare the pictures of different scales,
Yes.
maybe this could be a handle in order to understand what could be the solution?
Yes. In the case of these pictures, there's not so much you can do because you don't, how do I say it? The clusters of galaxies that we see here are sufficiently distant that they're not resolved by the lensing map. So you only see it's a peak. I mean, as I was coming into Torino, it was cloudy, and I could see the peaks of the Alps above the cloud, and I thought, wow, that looks just like the lensing map, and then you see these clouds that are there that are artificial peaks, and things like that. But, so you don't know the details of the peak. You don't know the outskirts and how they rise. So there are real tests. There are very sophisticated, so in the outer regions of clusters of galaxies where they're still forming, there are tests that you can make if you can measure the dynamics and you're really sure of what's in the cluster and what's in the background, and if the cluster is large enough on the sky that you can make a resolved lensing map. So in fact, yes, you can do that, but you need better data than this. And so people have actually been working on that, Antonaldo among them, and hopefully at some point we will have data that will be able to make these tests.
Any additional question?
Yes, sure.
And this one is not related to Lagrange or Einstein. You mentioned some exchange of letters correspondence between people and...
Zwicky.
Yes,
Yes.
Zwicky. Zwicky was a great physicist,
Yes.
but also a rather extravagant
Did you
person.
ever meet? Did you meet him?
I wonder whether I wonder whether there is some official archive
for
reporting
Zwicky?
some of the correspondence of that period, which is very important for cosmology.
I don't really know. Somebody wrote a book about Zwicky recently, and I don't really know what happened to Zwicky's papers. When I was young, I was fascinated by Zwicky, and I used to collect stories about Zwicky. And so I don't know the answer to your question, but it just popped into my mind. I wanted to tell one other of these stories. So Ed Salpeter was a great physicist who worked with beta salpeter equations and so on. So once I was visiting Cornell, and I told Ed that I was fascinated by Zwicky. He said, "Oh, I have a great story about Zwicky." So he told the following story, that Ed, when he was a postdoc, he went to visit Caltech, where Zwicky was a professor of physics. And Ed was giving a colloquium. And in the middle of the colloquium, a voice boomed out from the audience and said, "When I was a boy, my aunt had a huge library, and it was full of nonsense, but none so extreme as what I've just heard." And Ed Salpeter, and I said, "What did you say?" And he said, I said, "You must be Professor Zwicky." So then Ed said to me, "I don't know who won." I said, "You did." So Zwicky really was a character. I mean, I never met him, but many of my contemporaries who were students at Caltech did meet him. And I mean, there are huge numbers of stories about him, but I really don't know what happened to his correspondence.
So apart from Euclid, in a couple of years we will have JWST.
Yes.
How important it will be for the kind of thing that you are studying?
Well, I think JWST, its primary goal is to look at the formation epoch for galaxies. So it has, I think it's a small field of view. So it doesn't have the whole point of Euclid and the next American mission that would compete with Euclid would be W first. Who knows if that will ever come to fruition. So you need a large field of view to do this kind of work. And so JWST is not really the instrument. And for spectroscopy, you have an advantage from the ground because you have big collecting areas. So for spectroscopy in the optical, you need to collect all those ancient photons, and so you have a big advantage with large telescopes with wide fields on the ground. Euclid and W first are really the instruments that will do this. Right now on the ground there are large imaging surveys. So the Subaru telescope, the Japanese telescope in Hawaii, has now the world's largest camera, and that camera images 2¼ square degrees of the sky at a time. And the images from that are just spectacular, actually. And in the best conditions on Mauna Kea in Hawaii, the imaging is within a factor of 2 of what it will be from Euclid.
But it will be more important for dynamics, perhaps.
Yeah, I think it's mostly important. I mean, it's very important for observing young galaxies in the infrared. So that's really its main goal. So that's, I mean, I haven't really worked on the high redshift universe per se. So so I worked on a very nearby universe and now the middle-aged universe. But so yeah, I think Euclid really is the instrument that will make a difference in this particular line of investigation.
Yeah. For the other people, it's important to remember that actually it will be built here in
oh yes,
in
that's
Torino,
I learned. Yes.
Euclid, I mean, in Thales Alenia space.
Yes, it's supposed to be launched in 2020.
Or
who knows?
Let's hope.
Yes, let's hope. But it's a Russian rocket. It has to launch it, so.
If we survive until 2020.
Additional questions? If not, I do have one, actually. We talk about instruments, but we have young scientists over there. And from a theoretical perspective, do you think is there any crucial questions that theoreticians are not asking themselves this period?
Well, I mean, one of the difficulties really is that, there are a number of difficulties. One is we have this model that's based on things we don't understand, dark energy and dark matter. So, one of the most important questions is, what are they? And what is the underlying physics? And another question is, how do we really find ways of measuring and testing that? So there are a variety of things we can observe that haven't really been used fully as tests. And I think many theorists aren't thinking. There's more and more of a separation, it seems, between the observations and the theory in certain ways. And I think that it would be important for theorists to really ask what can be observed and how can it be used to really test these models in an independent way. So I think there really are fundamental, we really have we have no idea what the dark matter really is, nor do we have any idea what the dark energy really is. And I think the number of ideas that we have for testing that is not all that large.
No.
And so I think there's a lot of room for creative ideas to use the properties that we can measure of what we can observe to test these things. And there are lots of things that aren't used. Lots of dynamical quantities, for example, are never used. So, for example, this approach of using things with measured redshifts to compare the maps that you make with the lensing maps is not widely done. Part of the reason is that it costs a lot of telescope time to actually measure these redshifts. But people have the crazy idea that it's good enough to have lousy data and use that to try to measure something. And it doesn't tell you anything except what you already know.
Thank you. You can
There are
close it now. Question.
no other comments or questions. We may thank again Margaret. We congratulate her for the next degree that she's going to have on Monday. And thank you very much for coming here and to give us your talented, presentation. Thank you very much.
Yeah, thank you.